So is the mapping a function? And yeah, the answer is no, because with set A, which is your inputs, you got two arrows coming out of 4 right there, which makes it not a function. So again, that means that if you put in 4, you don't know if you're going to get 3 out or if you're going to get 7 out. Okay, we need to be able to know it's only going to have one value coming out if you put in 4. So we got 3 objectives here. The mastery quiz, which is next time, you don't have to write that down, but it's just a quick reminder that the stuff we're going over today, there will be a mastery quiz on next time. But the 3 objectives, I know the difference between independent and dependent variables. I can determine when a relation is a function or not. And I know what function notation is and can interpret it. So take a minute, copy those 3 down, then we'll get started. We've seen this slide already, mappings and functions. So yes, a mapping is just like a table, right? We got this is the mapping here on the right. So for example, we got the 2 columns. The one on the left is our input. And then the one on the right is output. So we'll probably see the machine again, but whatever you put in, the arrow tells you what's going to come out, right? So just like we've seen in the past, if, for example, 0 here, if it had 2 arrows coming out of it, it means that if you put in 0, you could get a 2 out or a 6 out, just like we saw on the bell work with 4. But again, a mapping like this is really just another way to write a table right here. So these are all ordered pairs. The arrows tell you each ordered pair. So of course, since there's not an arrow pointing from 2 to 2, or even, let's say 2 to 4, so they're different. So there's not an arrow pointing from 2 to 4, which is why in the table we don't see the ordered pair 2, 4. But these are all ordered pairs. Okay, so that's an ordered pair 0, 2. This is an ordered pair 1, 4, 2, 6, 3, 8, and 4, 10. All ordered pairs. So just like we saw on the bell work, when our mappings functions, it's when it's going to be a function as long as there's only one arrow coming out of each of the inputs. And it doesn't matter where they're pointing. So just like we've seen in the past, they can cross over each other. That doesn't matter. It just matters if there's 2 or more arrows coming out of one of these inputs, then it would not be a function. There we go. Okay, so again, the moment we see 2 arrows coming out of these inputs, it is not a function, just like we saw on the bell work. We got set A and set B. And before we get started here, we'll just quickly identify once again. We have an input, which is set A, and we're going to need this to fill in the blanks there. And then set B is our outputs. Okay, so that also means that your inputs, what we learned last time, that's our X values, and then the output, Y values. Which means also that each of these arrows represents an ordered pair. So from 7 down here to -3, that would give us an ordered pair of 7, -3. Or if you went from 3 to 8 here, that would give us an ordered pair, 3, 8. And then the last one here, 6, 5. If you put in 6, out comes 5. And these are all inputs and outputs. So this one, if you put in 3, you get out an 8. This one, if you put in a 7, you get out a -3. Inputs are X's, outputs are Y's. Now, again, I'm pointing this out. We got inputs and outputs. With some of the other classes, I made a mistake because I wasn't reading these properly. So make sure you take the time, read through them so you don't get the wrong one on this. So let's start. The mapping diagram represents a function, does not represent a function. This one, yes, it definitely is a function. And it's for the same reason that we saw on the bell work and on the last slide. Each of our inputs, 7, 3, and 6, only have one arrow coming out of them. Okay, if by chance there was 2 coming out of any of these, then we'd select that it does not. But they all do, so we can get rid of does not. This one definitely does represent a function. The next part is really asking why is it a function, but it's asking in a very nerdy way. So it says it is a function since there is one number or for each number. Well, we know we have to look not just at one of these values in set A, but at all of them, all 3 of them, because each number, so So we'll circle that one. In set A, because that's set A, that's our input here. And this is where we got to be careful because they've got set A here, right? Like right now I could get rid of the set B's. But set A, it's saying it's an input or is it an output? Well, since it's the left column here, it's an input, which we've already labeled. And this is where I was making mistakes before. Set A is an input. It is not an output. So we can cross that one out too. So for each number, let's go back here. For each number in set A, which is an input, there, it says it's talking about mappings. This is the arrows. When it's talking about mappings, that's the arrows. There's no mapping or multiple mappings. There's only one mapping. Well, there's only one arrow coming out of each of those. So it's not this one or this one. Okay, so let's read this as it is. We can get that last part. The mapping diagram above represents a function since, I got to cross this one out. Since for each number in set A, the input, where there is only one mapping, and to me, I think there's two answers for this. From set A, the input. But I think what they want on this one is to set B, which is the output. So see, I almost circled this one. But it's saying the input. Set B it's an output, right? We have this up here. So we know set B is an output. It should go to set B. Okay. It's saying the mapping. So the mapping is the arrows. Each arrow points to set B, which is an output. And that's all you'd have to do. You click on the boxes, you click on the correct selection, and then you just leave it there. When you finish, you push submit, and then it'll give you credit. This slide as well, we've seen this one too. So we're going to use the vertical line test if we ever have a graph. Okay, so vertical line is straight up and down like this line right here. And then all we're going to do is take this line and we're going to scan the graph. What we want to see from the graph is that as we scan it, and I like to go from left to right, but some students they like to go from right to left, and that's fine. But as I scan this, I'm just making sure that the line never goes through this vertical line test more than once. Because if it does, then it is not a function, all right? There we go. And that's what this is saying. Again, here at the bottom, we don't care if it's how straight the line is. It can be curved, it can be straight, it doesn't matter. It can be exponential, it can be linear, whatever you want to call it. We don't care when we're doing the vertical line test, okay? Determine if this graph is a function. So once again, we're going to use the vertical line test here, like this. And I'm going to take my vertical line, there we go, and I'm going to scan this line. So I can come to the line right here. I don't really care that it's got arrows on the graph line. I don't care about that. So I'm going to start here. I'm going to scan from left to right. So this is my leftmost point. I'm going to scan. Now remember, I don't care that it curves, meaning right here, from the arrow to this point here, it's going up, but then it changes direction going downwards, okay? I don't care that it does that. I don't care at all. All I care about is that it touches the line only once. So as I continue to scan, it changes direction again. I don't care about that. I keep scanning. What I notice as I scan this is that the line only goes through my vertical line once, ever, as I scan this, right? Like right here, it's going through the point 2, 0. Here it's going through the point 0, 0, and looks like negative 2, 0. Okay, so I have some roots, some x-intercepts. But I don't care about that. All I care about is that it goes through my vertical line only once. Since the graph only goes through my vertical line once, this one is a function. So determine if the graph is a function. I'm going to put yes. You could put a function, but that's up to you. So I've written this explanation. I don't think you have to. This is just kind of a yes or no question, function or no function, either one. We don't care that this has arrows. So there's it's kind of a crappy arrow, but there's an arrow there, and then there's the arrow there. I don't care. This just tells us that this pattern continues, meaning it goes upwards in this direction and then downwards in this for this arrow. So it's not going to suddenly change direction. This one is still a function, even with the arrows. If it didn't have the arrows, it would still be a function too. All right, this graph, a little bit new, right? But it's a circle. Hopefully that's okay. It doesn't matter, right? We're just going to do the vertical line test on this one. Let's get our vertical line out here. There we go. And then again, we're going to scan this. Now, I know some of you guys looking at this can figure out that it is or is not a function. But as I scan this right at the edge, you could say it's touching once. But the moment I get anywhere inside that circle, and I'll stop right there, boom, you got the graph, which is a circle, going through my vertical line twice at these 2 points. So since it goes through twice, it is not a function. One of our objectives here, we got a function notation. So we need to know what it is. Function notation is this. Now some students say this is f times x because of the parentheses. It is not. This is a new way to write y. Not the question y, but the letter. Y is the same as f of x. If you see this, again, it's not f times x, it's not f parentheses x, it's f of x. So if you want to really impress a math nerd, you read this as f of x. Now I know that sounds detrimental, right? Like, who wants to impress math nerds? But if you want to make yourself look really smart, just tell people this is f of x. And I'm like, what the crap? But in any case, the f does not mean f like you see it on bathroom stall walls. F in a math class means function. F is function. This reads function of x. So when you see f, it's function. Now, do they always use f? They do not. Sometimes they use g, sometimes they use a or z. It doesn't matter what letter they use. If you see it with a letter and then another parentheses, it's a function. It's function notation, okay? So how does this help us? Well, I don't know. Math people tend to change things that mean the same exact thing in order to make themselves look smarter than they are, right? Because here, this is y is the same as f of x, meaning that in the past what we've seen is y equals something like 3x plus 5, right? So this would have a slope of 3 and a y-intercept of 5. And that was great, and we loved it so much. Not so much. But what they're going to do now is they're going to take this exact same equation, and they're going to say it equals 3x plus 5. So notice that doesn't change. But instead of writing this as y, they're now going to write it as f of x. Now, the reason why math people like this so much is it tells us which one's dependent and independent in terms of the variables, which hopefully you remember from either 7th or 8th grade science class, which I don't remember which one it is, but they usually cover independent and dependent variables. But the f of x here, this is telling us that the function depends on the x. Okay, so that tells us that y is a dependent variable and x is independent, meaning x is something that you put in to the function. You put this in and then out comes something else. That's why the y, or the f of x, depends on what you put in. That's what that's explaining here. Y is dependent, x is independent. We'll talk more about this later, the independent-dependent thing. But for now, just with the notation, if you had f of negative 12, like this one is showing, this reads f of negative 12. Well, it used to be f of x, right? The original notation is f of x. But now instead of an x, they're saying f of negative 12. In other words, this tells you here that the x actually is negative 12. So this also means that when you see an x in the equation, that's what it's saying down here at the bottom, when you see x in an equation like this one, you can replace the x with that value. So in other words, if I were to take that x and replace it with negative 12, that means I can replace all the x's with negative 12. There we go. Okay, so now, is this hard to calculate? If it is, that's fine, but your calculator would like to do it for you. So just put this into the calculator, then you'd find f of negative 12. And that would tell you its corresponding y value. That actually gives you an ordered pair. We'll talk more about that later too, but this isn't necessarily supposed to be new because you're supposed to have a little bit of this background from 8th grade, but no one remembers anything from 8th grade, so that's understandable. Here's our machine again, because I guess we like it so much. Now the example that we've seen already, right? This is going to give us ordered pairs. So we're going to put something in. Now last time we put in 2, and we said, let's say out comes a 4, right? So this would give us an ordered pair, 2, 4, like this. Okay, and then we said, let's take those out. And let's say that we put in a 3. And then what would come out? Let's say 6. Now, some of you notice what's going on here with this pattern. But that would give us the ordered pair 3, 6. Let's say we're not completely sure yet. So let's put in another x value here. Okay, so let's take this out. Let's replace x. Let's say we're going to put in a 5. All right. So if I put in a 5, I can expect to get out a 10, just based on the pattern. So that gives us an ordered pair, 5, 10 here at the bottom. But what is the machine doing to your x? What is it doing to the x that you're putting in here? You're going to take the x, and you're going to multiply it by 2. So 2 times x is your function. It's the function machine. What's happening in this machine is it's going to take your x, and it's going to multiply it by 2, and then it's going to spit out whatever the y is. All right? Now, of course, like I was saying, you could write the equation as y equals 2 times the x. But since this is a function machine, and since math people like to change things that mean the same, we're going to show it as f of x equals 2 times x. Now, can you still write this as y equals 2x? On paper, yes, but I suppose on the assignment, probably not. So just be careful with that. So just to reemphasize the independent and dependent thing, right? I had the 5 already. Let's say it was $5, right? I had the $5 already in my hand. So that was independent. Then I put it in. The machine did its work, and then out comes the output, the $10, which is why the $10 depends on whatever I put in. Now, later on, they're going to say, well, put in 5 monkeys, and then out comes 10 rhinoceroses. I don't know what they're going to say. But it would still tell you that something that comes out will depend on whatever you put in. Okay, and it does have to go in this order. Independent happens first, dependent happens second. So this example right here, when f of x equals 2 times x to the power of 2 minus 8x plus 3, here's our equation. It says evaluate these two. So we're going to use the same exact equation for both of these functions. It's the same function for both of these x values, is what I should say. So let's write out the function. There's our function. But up here, it's saying f of negative 2, right? So it's saying x is negative 2, meaning take all the x's in the equation, replace it with negative 2. So that's what I'm going to do. I'm going to take this x, and instead of x, I now know it should be the value of negative 2. But there's this other x right here, right? With the 8x, the negative 8x. So I'm going to take that x and replace it also with negative 2. So here's the thing that we get sometimes from students is they look at this and they're like, that looks like garbage. I hate it already. And that's, again, it's understandable because it's math. But we don't expect you to do this in your head. We don't expect you to even use the order of operations to solve this. We expect you to use a calculator to do it, all right? So the exponent 2 here, sometimes this is what throws students off. If you look, just see the 7 right here? 1 to the left, you see a log, and right above that is x squared. To get that exponent, you're going to push the x squared button, okay? So let's put that in the calculator. Boom. So again, we just put this all into the calculator, and we get 27, okay? So in other words, f of negative 2 is going to equal 27. Boom. Now, of course, not that we're concerned about this right now, but this would be the ordered pair, negative 2, 27. So in other words, we put into the machine negative 2, right? We plug this in to the machine, and then it pulls out 27. There it is. Now we're going to do the same thing with f of 0. So again, the same exact function, 2x squared minus 8x plus 3. But now they've changed the x value to 0. So x for the second part is going to be 0, but same function, okay? So take the x's, let's replace those with 0. So that was 2x squared, but the x now is 0. So 2 times 0 to the power of 2, and then minus 8x, so that x becomes a 0 as well, plus 3. So once again, we'll put this into the calculator, and that will give us f of 0. This one's not too bad. I'll show you why this one's easy to do in your head. is because anything times 0 is 0, which makes 0 a very nice number to work with. But 2 times 0 is 0, even if you multiply by 2 zeros. 2 times 0 is still 0. And then 8 times 0 is 0. 0 minus 0 is still 0. Pretty much I'm just canceling out these two terms, and then I just end up with that 3 right there. So once again, this would end up being the ordered pair, 0, 3, which you could put on a graph, okay? But once again, the machine, right? I put in 0. It told us to put in 0 from the beginning. I put it into the machine, and you could put this all into the calculator. It punches out 3. So the y value is 3 when your x value is 0. Now this next part, you're going to see this on the assignment too. We have to fill in the blank with less than, that's this one, less than, greater than, or equal to. And we know f of negative 2, we got out 27. And then f of 0, when I put in 0, I got out 3. Really, we're just comparing these two values. It's doing it in function form right there. I don't know about you, but I'm pretty sure that 27 is bigger than 3. So I'm going to put a greater than symbol. This reads right here, 27 is greater than 3, which means also that f of negative 2 is greater than f of 0. So I suppose what they're looking for here is for you guys to make the mistake and see negative 2 and 0, because negative 2 is less than 0. But it's f of negative 2, okay, which is actually 27. So in this case, f of negative 2 ends up being bigger or greater than f of 0. Here we got if f of x equals 1/3 x minus 8, determine x. I didn't write this wording, by the way. Someone else did. It sounds funky to me as a math person, but I could be wrong. Determine x when f of x equals negative 14. See if you can do this one. It's a little different. See if you can do it, then we'll go over it, okay? Whatever. So determine x. This is saying find the x when f of x equals negative 14. Remember what we said. F of x is actually just y. It's telling us y equals negative 14 right here, okay? And in the equation, f of x right there, that's another way to say y, right? So for the function, let's show that right there. F of x equals 1/3 x minus 8. So common mistake here, since we haven't done this very much, right? Students say, well, this tells us that x is negative 14, but it doesn't. Okay, do not replace this x with 14. This is telling us that the y, or f of x, is 14. See the f of x right there? This is f of x. It's negative 14. Let's take that f of x right there, replace it with negative 14. Now, since we love solving equations so much, this has now caused so much joy in our heart. And we are ready now to solve it with principles of equality. So that is what I will do. So principle of equality first. I want to isolate my x's. There's no distribution, which is great. No combining like terms. But here on the right, I've got this minus 8, right? The negative 8. I don't want that with my x's. My 1/3 of an x, by the way. So I'm going to get rid of it by making it a 0. Let's make it plus 8 right there. Now, it is a principle of equality. So if I do it to one side of the equation, I've done it on the right side of my line. I've got to do it on the other side as well. So I'm going to have to plus 8 there. Now, let's work from left to right. Negative 14 plus 8. You can put that in the calculator. You get negative 6. This would equal the 1/3 x. We didn't do anything to that, so we're just going to drop it. 1/3 x. And then negative 8 plus 8 is 0. It zeroes out just as we planned. And just like people that are zeros, we can ignore it. Okay, so this 0 right here, we're going to ignore it, even though it's right there. You just can't see it. It's called a phantom 0. Last thing we want to do is to make the coefficient of x 1. Right now, though, it is 1/3. So how do we make a 1/3 a 1? You just divide it by itself. Okay, so I'm going to divide that by 1/3. I'm going to take negative 6 and divide it by 1/3. So when you put this into the calculator, since we don't have the n over d button, you got to put parentheses around your 1/3. Because if you don't, then the calculator is going to give you, well, it's going to do it correct, but it's going to give you the wrong answer because it's doing it by the order of operations. If you don't put the parentheses around it, I believe you'd get negative 2, which is incorrect. The answer is not negative 2. When you put parentheses around this, then we're going to get the correct answer. In the calculator, when I put this in, I'm going to use the n over d button to make the 1/3. Negative 6 divided by n over d, 1/3. And you will get, in your calculator there, negative 18. Okay, and then 1/3 divided by 1/3 is 1x. So x here equals negative 18 if the y value that we start with is negative 14, which again would give us an ordered pair of negative 18, negative 14. Okay, so in other words, this problem gave us the output in the beginning. We had to backtrack using the function in order to figure out what was put into the machine at the beginning. Okay, it gave us an output of negative 14. We found that if you get negative 14 out, you had to have put in a negative 18 in the beginning. So this one's very similar to that last one. Again, this is not telling us that x equals negative 17. It's telling us that f of x equals negative 17, which is another way to say that y equals negative 17. So this is the same, similar to the last one, is it's telling us what's coming out of the machine. But we know what's happening inside the machine because it gave us the function as well. Okay, so let's rewrite that function. So there we go. It's exactly the same function that we have here at the top, but instead of replacing the x with negative 17, I'm going to take the f of x and replace it with negative 17. So let's get rid of that. Let's replace it with negative 17. And oh, the joy from Unit 1, solving equations again, right? In fact, this one, only 2 steps, which really isn't too bad. So let's take this. Let's isolate. That's a negative x. In fact, you could show it as a negative 1x if you want. But I don't want that plus 15 with my negative 1x. So I'm going to zero it out. I'm going to make it a 0 so I can ignore it. So I'm going to subtract 15. But if I do it to one side, I got to do it the other side as well. So from left to right, negative 17 minus 15, this would be negative 32, which you're welcome to put in the calculator. And then I got my negative 1x, which I can now drop. And then finally, 15 minus 15 is 0, just as we had planned to get rid of it. Okay, so it's gotten rid of, it's still there, right? It's still right here. It's just we can't see it anymore because it's a 0. And zeros we get to ignore. The last thing we want out of this is a positive 1x coefficient, positive 1 coefficient. So we're going to take this negative 1, and we're going to force it to do what we want to do and make it a 1. So to make it a 1, you're going to take it and divide it by itself. Right, so again, this is principles of equality, but as I've shown, I've done it on the right. I also must do it on the left as well. Negative 32 divided by negative 1, put that in the calculator, positive 32. So determine x when f of x equals negative 17. Well, x then would be 32. And just to emphasize this once again, this would give us the ordered pair 32, meaning if you put 32 into this function machine, you would get out negative 17. Function notation and graphs. So remember, f of x equals some number. This is the same as y. So it's just telling us again that if you wanted to see this as y equals, you can rewrite it if you wanted to, okay? So in other words, f of x equals 10 means y equals 10, just like we saw in those last examples. This is 10 on the y-axis, the y number line. Okay, so on a graph, you just find this value, whatever it is, on the y number line, and then you find the corresponding value on the graph. That may not make a lot of sense right now, but hopefully it will later. Now, if it tells you what the f of some number is, that's not a hashtag, by the way. In my generation, that was a number sign. F of some number means x equals that number, just like we've seen. So if we saw f of 4, this means x equals 4. So we can go to the x-axis and find 4 on it, and then find where the corresponding value is on the graph. Again, I worry because it's not really demonstrating anything, but it's saying it out loud, and it's kind of nerdy, so we tend to struggle with that kind of stuff. Let's see an example. So the graph of y equals f of x is shown. It's just a bunch of ordered pairs, right? We got C, A, D, and B here. But it says which point could be used to find f of negative 4. This is telling us here that x equals negative 4. So in other words, I need to find on my x number line, the horizontal number line here, x number line, I need to find negative 4. So negative 4 is, I found it, it's right there. Okay. What I got to do is find if there's any point on this line that represents x is negative 4. So I can see I would have to go down here to get to that point. It's this one, C. And that's even the ordered pair, -4, -7. But again, it's showing that the x value is -4. So if you wanted to, you could do this in a little different order. You could go through all the ordered pairs and just all these points and list their ordered pairs like I just did right here. And that may help you. But x is -4. If you put that in this function, you get out -7. So which point could be used to find f of -4? That is point C. So the next point, which point could be used to find f of x equals -9? So this one's telling us that y equals -9. So again, y equals -9 means that I've got to use the y number line, and I'm going to follow this down until I find -9. Boom, I found it right there, right? So here's -9. And yeah, it's almost pointing to the point that's on that line right there. That's point A. Now the ordered pair for point A is 1, -9, which I'm just doing again to show that the y value actually is -9 for that ordered pair. So which point is that? It is point A. So right here, right off the bat, evaluate f of -4. Again, I don't care that there's a line here. I'm just going to figure out this x value and this y value because it's f of -4, which tells us that the x is -4. So on my x number line, my horizontal number line, I'm just going to scan for -4. I found it. So let's mark it. -4. Now I see to get up, to get to the graph, I've got to go up here. Okay, so I'm going to follow that line up for -4. I see it's at this point, which has, at least right now, the x value is -4. And then I follow this over to find its corresponding y value, that's 2. Okay, so right off the bat, it was saying, well, x is -4. So you're going to put into this machine, x is -4. And then what'd you get out? I got out a 2. So the answer to this, f of -4 equals 2. So that's all you put in the box. And that comes from that ordered pair, -4, 2. Okay? The next part, f of x equals 3, tells us that y equals 3. So since it's y equals, because y is the same as f of x, I'm going to use my y number line. That's the vertical number line here. And I've got to find where y is 3. So I'm going to scan this down. I'm going to 8, 7, 6, 5, 4, 3. There it is, 3. Let's mark that one as well. So I follow this line over till I get to the graph, which is right here. So it is that ordered pair. Now that's a y value that's 3, so I'd have something 3. But the first value is what we put in. Out came the y value, which is 3, which is what that was saying. This is that the output is 3. So what do we put into this? Well, we go back down here, and I can see that that corresponding x value is 2. So solve f of x equals 3. The answer there is 2. Dependent is y values. And again, we saw this a couple slides back. But dependent is y values, which means this is your output. So in the machine down here, we know we put something in, something comes out. That's an output. That's our y values, which is now what we know to be dependent. Independent variables are the x values, or x's. And that is what we put into the machine. That's input. So this first sentence right here, it may seem kind of redundant, but dependent variables will change because of independent variables. This should make sense with the machine. What comes out will depend on what you put into the machine. You put something in, and then you can figure out what comes out. So yeah, our input there is independent. There we go. So also, what we'll kind of find with this is since y's are dependent, independent values are, at least with word problems like the ones we're going to be seeing in these next few examples, in the context, independent variables or values, they have to happen first. And then, just like the machine, once you put it in first, you put something in, then second, you can find out what comes out. So dependent variables in order in these word problems, generally independent happens first, dependent happens second. So like this example here, your grade depends, so it's telling you that the grade is dependent, by the way. Your grade depends on your assignment, quiz, and test scores. Your grade changes because of your scores. It's saying the same thing, right? So your scores have to happen first. So first, on this one, you would have some kind of assignment, quiz, or test score, which makes these independent. The scores are independent. And then once you have a score, then you can figure out what your grade is, which means the grade depends on the scores. Okay, so yeah, the dependent, the grade happens second. Now you could simply ask yourself, which value depends on the other value, but generally speaking, students do better if they understand the order of things. So yeah, independence usually happens first. That's what it's saying. This next example, it says, the number of calories you consume increases as the number of bacon strips you eat increases, which I guess makes sense. But in any case, here, the bacon strips, you have to eat the bacon strips first, and then you can figure out how many calories you've taken in, that's consuming, right? So in this one, same idea. The bacon strips has to happen first, which makes it independent. And then you can figure out how many calories you'd get out of that. So that's what makes the calories here dependent, because they happen second. So again, just going back to the machine. In the machine, for the first example here, you would put in a score, and then out comes a grade. It has to be in that order. You wouldn't put it in a grade, then out comes a score, because there could be lots of them, by the way. Or this one, right? You put in bacon strips, and then out comes the number of calories you've taken in. The amount of gas your car burns changes with the speed of your car. To determine which one's independent and dependent, let's just look at the two values we're comparing here. We got the amount of gas your car is burning. So it's burning gas, not how much is in the tank. And then also we're looking at the speed of the car. And for all these, we should only be comparing two things. So again, which one happens first? Well, based on what we're looking at, the amount of gas your car burns, if I were to think about this as a question, which one is depending on the other? It looks to me like the amount of gas your car burns is depending on the speed of the car. So once you know your speed, which means that it would have to happen first, then you can figure out the amount of gas your car is actually burning, which means it would have to happen second. Okay, so in your machine, the car, you put in a speed, out comes how much gas you're burning. Boom. So right away, we can label these as independent and dependent. All right, so we have those two. These next two, as the amount of rain increases, so does the water level of the reservoir. And then the last one, you weigh a box that has some books inside. So again, figure out which two you're comparing on these. Figure out which one's independent, dependent. Take 30 seconds. See if you can do these ones on your own. Then we'll go over them. So this first one, we got two things that we're going to compare, right? We got the amount of rain, and then we got the water level of the reservoir. So again, you should think which one happens first, which one happens second. On this one, the amount of rain happens, and as the rain, it's because it says it's increasing, but as the rain falls, it will definitely change the water level of the reservoir. Okay, now you could say, well, the water level of the reservoir was there already. That's true, but since we're comparing it with rainfall, between the two, you would wait till the rain finishes falling, and then you would take the water level of the reservoir. So the amount of rain in this case that is increasing, that's going to happen first, which makes this independent, and then the water level of the reservoir is going to happen second, which makes it dependent. All right, this next one, you weigh a box. So we're looking at the weight of a box, and we're looking at the number of books inside. So again, we look at this, we got the weight of a box and we got the books that are inside. So for this one, you'd have to first figure out how many books are inside, or you'd have to put them inside the box actually. And then after you put the books inside the box, then you would weigh it. Now we don't know if they're doing this right, if they're just putting it on a shelf or if they're sending it to someone, we don't know. But still, the weight of the box will have to depend on how many books are inside of the box. So there we go for these three. And I'll just point this out. Notice that the first example was dependent, then independent, then it was independent, dependent. This was independent, dependent. Don't always expect these to be in the same order. You have to actually think about these, which one is independent, which one's dependent. So if we've made some mistakes today, that's okay. We're still just learning how to do this, but you'll get some more opportunity to do this on the assignment as well. Let's try this example, because again, this is the way it's going to look like on the assignment, right? You're buying donuts for a family gathering. Each donut costs $1.75. Answer the questions below regarding the relationship between the total cost and the number of donuts purchased. All right, so we got two things that we're comparing first on this, right? We're comparing the cost, and then we'll look at the number of donuts purchased. Okay, two different things. Again, which one has to happen first on this one? And we need to think about this because it's asking right off the bat, the independent variable X represents, you got the two things, you got the cost and then the number of donuts. Well, between these two, the one that has to happen first would have to be, you have to know how many donuts you're going to purchase first. So for this one, we're going to say donuts purchased. That is independent, right? Because it happens first. And you can think about this as well, right? How much are you going to pay? Well, it depends on how many donuts you purchase. Okay, there's that word depends. So the independent variable X represents the number of donuts, and the dependent variable has to be the other one just by the process of elimination. But again, the total cost will actually depend on how many donuts you have purchased. Because we got two options here. Something depends on, the cost is dependent, so it will depend on the number of donuts that have been purchased. Okay, so a function relating these variables is n of x equals, I guess we got to fill in this blank right here, right? Okay, so the n is a function based on the number of donuts you purchase, and that's why they're using n instead of f. But it's a function of x. Here's the thing, is we know up here at the top, you're going to spend $1.75 on every donut. It doesn't say that you get a deal for purchasing a dozen or anything like that. So I'm going to take $1.75. Now, if I have $1.75, that's only for one donut. If I bought two donuts, I'd have to add it to itself. If I bought 3 donuts, add it 3 times. If I bought 4 donuts, add it 4 times. That's just multiplication right there because it's repeated addition. I'm just going to multiply that by x. That is the function right there. Now, if by chance on the assignment they give you some kind of starting value, then you would have to like add it or maybe even subtract it, depending on how it's worded. All right? Okay, but that's our function. N of x equals 1.75x because each donut is $1.75. And the $1.75 is a slope or a unit rate. And at the bottom it says, so n of 15 equals blank. So this means, here at the bottom, you're going to buy 15 donuts. Now, to some people that sounds like a lot of donuts. To me, not quite enough. But in any case, I'm going to take, let's write this out here. I'm going to do this on the left. So our function, n of x, 1.75 times the x. But now here it's saying, you know what, take your x and make it 15. So you're purchasing 15 donuts. Now I think some of you may not have used the function for this. You would have just taken 15 and multiplied it by 1.75, but I'm going to do that with the function anyways. And as much as I wish I could, I cannot do that in my head. But if you purchase 15 donuts, how much will it cost? Okay, so 26.25, that means if you're going to purchase 15 donuts, it'd be $26.25. That's it. So again, you put in 15 donuts, out comes a cost of $26.25. Boom. Well, I should put that in here, right? 26.25. Meaning 15. Oh, we got this. We got some options here again. There we go. So that means it will be 15 donuts. 15 donuts will cost. Well, I guess we got that as $26.25. 26.25, and that would be dollars. That's it. That's our objectives again. I know the difference between independent and dependent variables. We did that towards the end. Can we tell if it's a function or not? That was kind of with the graphs and let me see some tables maybe. Whatever. I know what function notation is and can interpret it, and we do that in the context of independent and dependent variables too.